Alright, so now that we've completed our warm-up by showing that at the very least PRIM's algorithm outputs a spanning tree, let's move on and actually show it outputs a minimum cost spanning tree. And to prove this theorem, we're going to have to tackle head-on the kind of crisis which you always face when designing a greedy algorithm. So in a greedy algorithm, you're making an irrevocable decision. Like in PRIM's algorithm, we're including an edge in our tree and never revisiting it later. And how can you be sure that you're not making a mistake? How can you have a guarantee that the decision you're making seemingly myopically right now is actually a good decision? It won't come back to bite you later. So it turns out for minimum spanning trees, there's a beautiful condition which tells you when you're guaranteed to not regret including an edge in a spanning tree. That guarantees when an edge has to belong to the minimum spanning tree. So that's called the cut property. It's the subject of the next slide. So this is a cool enough property that we're going to bestow it not just with all caps, but even with a box. Now, that's a pretty good property. So what does it state? Well, consider an edge of a graph, an edge that we are wondering if it's safe to include it in a tree so far. So here's the sufficient condition guaranteeing that you won't regret including this edge in the tree so far. The condition is stated in terms of a cut. So suppose you can find a cut A comma B with the property that amongst all edges in the graph G that happen to cross this cut, the edge E is the cheapest edge crossing this cut. Okay, so not only should our edge E cross this cut AB, but it should be the cheapest such edge. If this condition is met, then we definitely want to include the edge E in our solution. Indeed, the edge E has to be a member of any minimum spanning tree of the graph. So in this video, we're going to assume that the cut property is true. It is by no means obvious, definitely requires a proof. I'll give you the proof in a separate video. It's a little bit tricky. It's based on a subtle exchange argument. For this video, we're going to assume that it's true, however, and we just want to be clients of it. We want to figure out what it's good for. Now, I will soon show you that it actually implies correctness of PRIM's algorithm, but just to get a feel for it, let's look at it in a much simpler graph. Let's just look at a 4 cycle, 4 nodes, 4 edges with edge costs 1, 2, 3, and 4. So let's look at a few cuts. So let's look at the cut where on one side of the cut I put the upper right vertex, and on the other side of the cut I put the other 3 vertices. So there are 2 edges crossing this cut, the edge that has cost 1, the edge that has cost 2. So the edge with cost 1 is the cheapest edge crossing this cut. So by the cut property, the edge of cost 1 has to be in the MST. Okay, so we looked at one cut, invoked the cut property. It told us an edge to stick in the MST. That was pretty cool. Let's look at another cut. Let's look at a cut where on one side we just put the bottom right vertex, and on the other side we put the other 3 vertices. Now this cut has 2 edges crossing it, the edges that have costs 2 and cost 3. The edge of cost 2 is the cheapest edge crossing this cut. So by the cut property, it has to be in the MST. So that's cool. So we know the 2's got to be there. Now let me point out something interesting that's happened, which is that it is not the case that this edge of cost 2 is the cheapest crossing every single cut that it crosses. Remember when we looked at cut number 1, this edge of cost 2 is actually the most expensive edge crossing that cut. But we found a different cut that is the cheapest crossing, and that's enough to justify the cut property. So in other words, all that's important for the cut property, I just got to find you one cut for which an edge is the cheapest. That's enough to conclude its presence in the MST. So similarly, we can look at a third cut, just consisting of the bottom left vertex and the other 3 vertices. And it's the same story. There are 2 edges crossing this cut, the edge of cost 3, the edge of cost 4. The edge of cost 3 is the cheapest edge crossing this cut, so we know it's got to be in the MST. And again, when we looked at cut number 2, it didn't tell us whether or not the edge of cost 3 is in the MST, but when we looked at cut number 3, that was enough to conclude that the edge of cost 3 has to be in the MST. So there we go. So we could use the cut property to construct an entire MST. On the other hand, there's no way to use the cut property to try to justify the edge of cost 4. Any cut that you pick for which the edge of cost 4 crosses, there'll be some other cheaper edge crossing it. So you can never use the cut property, as one would hope, to justify the inclusion of the edge of cost 4. And you better not be able to, because 4 is not in the MST. Now, a quick side note, some of you might be wondering what I wrote in the conclusion of the cut property. I said the MST of G. So that would seem to indicate that the minimum spanning tree is unique. So that deserves a quick comment. So first of all, if the edge costs are not distinct, if you have ties between edges, then you can certainly have multiple different minimum spanning trees, and you have to state the cut property a little bit differently. But again, in the lectures, we're just going to assume distinct edge costs, so that's not a problem. And in fact, something that'll be a consequence of the next slide, we'll notice that the minimum spanning tree is unique with distinct edge costs. It's not obvious, but we'll prove it shortly. All right, so what I want to do to finish up this video is I want to assume that the cut property is true. And then from that, I want to argue that Prim's algorithm is correct. Always outputs an MST. The proof of the cut property is non-trivial and deserves its own video, which you can see separately. All right, so given the tools that we've developed, this argument's actually going to be quite short. So let's assume that the cut property is a true statement. And let's begin by building on the previous video. The previous video argued that Prim's algorithm outputs a spanning tree. It didn't argue it was a minimum one, but it argued that it's a spanning tree. It spans all the vertices and it has no cycles. Let's call the output of Prim's algorithm at the end of the algorithm T star. Now, stare at the cut property. Stare at the pseudocode of Prim's algorithm. What happens in each iteration of Prim's algorithm? Well, we have our set capital X. That's what we span so far. There's the rest of the stuff, V minus X, so that's a cut, X, V minus X. What does Prim choose to include next? Well, it brute force searches through the edges that cross this cut, and it adds the cheapest one of them. Well, that is right in the wheelhouse of the cut property. What does the cut property says? It says cheapest edges crossing cuts have to be in the MST. So they just fit together beautifully. Prim's algorithm explicitly picks an edge at each iteration, which satisfies the hypothesis of the cut property and therefore has to be in the MST. So remember, the conclusion of the cut property says edges so justified must belong to the MST. So if everything in T star is justified by the cut property, then everything in T star is in the MST. So T star is a subset of the MST. But T star, of course, as we've argued, is already a spanning tree in and of itself. And if you add more edges to T star, it's no longer going to be a spanning tree because you're going to pick up cycles, right? If you ever have something that's connected, there's a path from each pair of vertices, and you add a new edge, you're going to close a path, you're going to get a loop. Okay, so T star is already a spanning tree, and you can't have anything bigger and still be a spanning tree. So therefore, this has to be the minimum spanning tree. There cannot be anything else. So for this reason, T star must, in fact, be the minimum cost spanning tree of the graph. Since the input graph was arbitrary, assuming only it was connected, this completes, assuming the cut property, the proof of correctness of Prim's minimum spanning tree algorithm.